Bismillahirrahmanirrahim. Assalamu alaikum. My name is Nabil Jafar and my second group member name is Usman Azim. Our topic is polymerization. It will cover the main contents as what is a polymer, its different classes, its laboratory and biological synthesis, its properties, its classification, its synthesis of rubber. First of all, what is a polymer? A polymer is a large molecule. You can say it is a macromolecule which is composed of repeating structural units. These subunits are typically connected by covalent chemical bonds. Although the term polymer is sometimes taken to refer to plastics, it actually encompasses a large class of natural and synthetic material with a wide variety of properties. For example, we have a monomer A. Then thousands of monomers of this type A would connect to give a. The background of polymer is that its main class is macromolecules, which is divided into two classes, inorganic and organic one. In inorganic we study the structures of diamond, graphite and sand etc. Whereas in organic we study the structures of biopolymers and synthetic polymers. Biopolymers includes lipids, proteins, carbohydrates and nucleic acids etc. Whereas synthetic polymers includes plastic, synthetic fibers and rubber etc. So our main topic is the organic one. Now the laboratory synthesis methods. First one is step growth polymerization and the second one is chain growth polymerization. The step growth polymerization is also known as the condensation polymerization where the monomers may combine with one another directly, whereas in chain growth polymerization, which is also called addition polymerization, monomers are added to chain one at a time only. Synthetic polymerization reaction may be carried out with. For the biological synthesis of the polymers, there are three main classes of biopolymers which are used. First one is polysaccharides, second one is polypeptides, and the third one is polynucleotides. Many commercially important polymers are synthesized by chemical modification of naturally occurring polymers. The base is therefore the naturally occurring polymers. Prominent examples include the reaction of nitric acid and cellulose to form nitrocellulose and the formation of vulcanized rubber by the heating of natural rubber in the presence of sulfur. There are different properties of the polymers. First one is constituent monomers, which is depicted by the identity of its constituent monomers. Second one is microstructure, essentially describes the arrangement of these monomers within the polymer at the scale of single chain. The chemical properties are at the nanoscale. It describes how the chain interact through various physical forces, whereas at the macroscale they describe how the bulk molecule polymer interacts with one another, chemicals and solvents. There are different mechanical properties of a polymer. First one is tensile strength, its Young's modulus of elasticity, its transport properties, its phase behavior, for example melting point, glass transition temperature, and mixing behavior. According to structure and some properties, polymers can be classified into two categories, namely linear polymer and the cross-linked polymer. In linear polymer, the chains can be stretched, which causes them to pass each other. When released, the polymer will not return to its original form, whereas in cross polymer, if the chain is stretched, the polymer can be returned to. Here is a method to calculate the molecular weight of a polymer. It is equals to molar mass of the repeating unit into the degree of polymerization. Degree of polymerization is the number of repeating units. A repeating unit, for example in linear polythene, is CH2 bond CH2. Therefore, if the degree of polymerization of polythene is 1000, then its molecular mass would be molecular mass of the repeating unit into the degree of polymerization. Here the molecular mass of the repeating unit CH2 bond CH2 is 28 into 1000, which is the degree of polymerization, which gives the result 28,000. So the molar mass of the polymer is 28,000. Most high molecular mass of the polymers are useful for making plastics, rubbers or fibers and have molecular masses between 10,000 to 1 lakh. There are different classes of polymers. The two broad and main classes of the polymers are the homopolymers and the copolymers. Polymers are further classified by the reaction mode of polymerization, which include addition polymerization and condensation polymerization. Classification, which is based on the physical properties related to heating, are thermoplastic and thermo. First one is homopolymers, which consist of chains with identical bonding linkages to each monomer unit. This usually implies that the polymer is made from all identical monomer molecules. This may be represented as if we have the monomer A, then the long linkage of A units would give rise to a homopolymer. Now the second class is copolymers, which consist of chains with two or more linkages, usually implying two or more different types of monomer units. These may be represented as AB, AB, AB and so on, where A and B are the two monomers. Now my next group member Usman Azim will further elaborate you about the addition polymerization.
Assalamualaikum. As Nabil have told you that polymers are also divided according to the reaction mode. The first type of this classification is addition polymerization, in which the monomer molecules bond to each other without the loss of any other atoms. Alkene monomers are the biggest group of the polymer in this class. We know that addition polymerization is a chain reaction, so it will involve some steps to continue. The first step is initiation. In this, the free radical indicator attacks silane and breaks a double bond and form an activated monomer. The second step, propagation. This activated monomer reacts with the silane and form a growing polymer chain. The last step, we stop the reaction by reacting two free radicals which they form a stable bond. The second type is condensation polymerization, in which usually two different monomers combine with the loss of a small molecule like water. Polyesters and polyamides are the two examples of the condensation polymerization. The monomer of condensation polymer has specific property about the functional group and the reaction site. In the figure, we can see that the monomer have two functional groups which are amides and carboxyl group. They form a link and then form a long chain of condensation polymers. The difference between addition polymerization and condensation polymerization are that in addition polymers, it follows the free radical mechanism. There is no side product involved in the addition polymerization. It is also a non-ionic process. It completes in three stages via initiation, propagation, and termination. The functional group is not involved in addition polymerization. The examples are polystyrene, polyvinyl acetate, polyvinyl chloride, etc. The condensation polymer follows no mechanism about free radicals. It has also side products like water and carbon dioxide. It is a completely ionic process. It has no stages, it is a single step process. The functional group is a basic part of the condensation polymerization. The examples of condensation polymerization are polyester resin, polyamide resin and epoxy resin, etc. The plastics are also divided according to the basis of their heating mode. The first type is thermoplastics. The plastics that soften when heated and become firm again when cooled are the thermoplastics. This type is the most unpopular type of plastics because the heating and cooling may be repeated again and again. The second type is thermosetting plastics. The plastics which soften when heated and can be molded but harden permanently are thermosetting plastics. They will decompose when reheated. This is because I can see in the figure that there is a cross linkages between the molecular chains. This is the main cause that why they are decomposed when heated again and again. An example, thermosetting plastic is bakelite, which is used in toasters, handles for pots and pans, dishes, electrical outlets, tires, rubber bands and billiard balls. Let us know what is the structure of natural rubber, which is an important polymer of isoprene. To understand the structure of rubber, we shall concentrate on the structure of isoprene. Isoprene is a conjugated diene containing double bonds at the alternating position. As you can see in the figure, structure of isoprene is a monomer of natural rubber. During the polymerization of isoprene, we may get cis polyisoprene or trans polyisoprene. The rubber formed from cis polyisoprene is also known as natural rubber. The figure of natural rubber is shown here. The the trans polyisoprene or synthetic rubber was obtained by the free radical polymerization of isoprene. The rubber so formed has all the trans configuration, but there is no elasticity property in the synthetic rubber. The figure of synthetic rubber is shown. There are some types of synthetic rubber also, which are neoprene, buna S, buna N, thiokol, and vulcanized rubber. Number 1. Neoprene. Neoprene is a polymer of chloroprene. It is also known as polychloropyrene. The chloropyrene reacts in the presence of oxygen and peroxide to form neoprene. The reaction is shown in the figure. The uses of neoprene are that it is used in manufacturing of hoses, gaskets, shoe heels, stoppers, conveyor belts, and printing roller, etc. It is also used as an insulator. The second type is buna S. Buna S is a copolymer of mixture of 1,3-butadiene and styrene in the ratio of 3:1 in the presence of sodium. In the figure, we see that butadiene and styrene react in the presence of sodium to form buna S. Buna S has a specific property that it is very tough and good substitute for natural rubber. It possesses high abrasion resistance. It has high load bearing capacity. So we use buna S in the manufacturing of automobile tires. It is also used for making floor tiles, footwear components, cable insulation, etc. The third one is buna N. Buna N is obtained by copolymerization of 1,3-butadiene and acrylonitrile in the presence of peroxide catalyst. The reaction of formation of buna N is shown in the figure. Buna N has a property that it is resistant to the action of petrol, lubricating oils, and organic solvents. So we use buna S in the making of oil seals, hoses, tank linings, etc. The fourth type is thiokol. Thiokol is prepared by the copolymerization of 1,2-dichloroethane with sodium tetrasulfide in the presence of magnesium hydroxide. The reaction of formation of thiokol is shown in the figure. Thiokol has a property that it is resistant to the action of mineral oils, solvents, oxygen, and ozone. The last type of synthetic rubber is vulcanized rubber. Vulcanized rubber is an improved form of natural rubber. We can get vulcanized rubber by reacting natural rubber by heating natural rubber in the presence of sulfur. In vulcanized rubber, sulfur bridges are introduced either at the reactive allylic site or at the site of the double bond. That was all from our side about the polymerization.